Hello, I'm Stefan Malewski, and I will present a joint work with Michael Greenberg and Eric Tante. This work is concerned with the application of gradual typing to data structuring. Gradual typing is all about working with imprecision. It does this by the relaxation of static typing to allow for a wider range of programs, transferring responsibilities from the type checker to the runtime through dynamic type checks, and in this process introduces the possibility of runtime type errors. Type precision induces the notion of type consistency, which is the gradual lifting of the type equality. Gradual typing has been explored in the context of different features, like union types, parametric polymorphism, ownership types, and CIC. But the concept of gradually structured data has not received as much attention in the literature. But what does gradually structured data mean? As gradual typing describes the continuum between static and dynamic typing, gradually structured data explores the space between structured and unstructured data. In the structured side, we have features like algebraic data types in OCaml, where you describe a structure of data with great detail. In this setting, constructors must be declared statically. The set of constructors for a given data type is closed at the point of definition, and constructors cannot be shared between data types. This enables software developing tools to check for exhaustiveness of pattern matches and well-formedness of constructors. In the other side lives tagged data, like seen in Scheme, where data is just tagged with a name. Tags, unlike constructors, do not impose any structure over the data, making the checks described before impossible. But this sacrifice comes with an increased flexibility, for example, by not restricting the possible cases in a match expression. Having defined these extremes, we can now ask ourselves, what kind of structures lie in between them? These structures should have a mix between the static guarantees of ADTs and the flexibility of tagged data. One example of a data structuring feature that lives somewhere in this continuum is extensible variants, like seen in OCaml. These variants are not closed at definition and can be extended from another module. They are just a bit more flexible than ADTs because although they can be extended after defined, constructors must be declared statically and they cannot be shared between data types. Another interesting feature, also in OCaml, are polymorphic variants. They are statically checked constructors that do not need to be defined before use. Sadly, they cannot interact with regular variants. They live in two different worlds. There is no way of, for example, mixing patterns from variants and polymorphic variants in the same match expression. This categorical separation makes polymorphic variants not well suited for small and gradual changes in flexibility. We propose gradually structured data, a discipline that supports programming in a broad spectrum of the continuum between unstructured and structured data, where statically declared constructors and unclassified or tagged data coexist and fully unstructured or structured programs are also supported. Let's see GSD in action. Imagine there is a server, the ellipse at the bottom of the screen, that expects constructors and matches on them. At this point, there is no data type, just free-floating unclassified constructor. As the cursor in the bottom left corner indicates, we are in a completely unstructured gradual program. The server knows how to work with some of these constructors, but its behavior is not defined for every possible one. For example, it fails for print. We introduce an open data type named color that statically defines two constructors, RGB and gray. In contrast to closed data types, open ones can be inhabited by free-floating constructors. For this reason, it's possible to call the server with black and print, passing the responsibility of checking if the server can handle these constructors to the runtime. Because color defines gray, it imposes a restriction on the type signature of that constructor, making the third constructor application a static error. Now, open data type definitions give us static checking of the defined constructors. The server now expects constructors of the type color, which includes free-floating constructors. To make things more structured, we introduce a new open data type called action, and print is no longer unclassified data. Since unclassified data can inhabit any open data type, it can be thought as if those constructors are shared by every open data type. In contrast, statically defined constructors, either in open or closed data types, cannot be shared. For this reason, calling the server with print now causes a static type error. Closing color seals the constructor set of the data type, allowing, among other things, for exhaustiveness checking. Unclassified data no longer can pass as if we're a member of the color data type, making a call to the server with the constructor black a static type error. Finally, we can make this program even more structured by closing every data type. This makes unclassified data a static error. Now we can have a completely static program. GSD is a gradual version of a simple static language with nominal algebraic data types. The language has two interesting features. It supports open and closed data types in the spirit of extensible variants, and it's parameterized by matching strategy, meaning that the formalization does not depend on the particular definition of validity for pattern matches. We identified three possible meanings found in the literature. In sound matches, every pattern must correspond to a constructor of the type of the discriminant. In complete matches, every constructor of the type of the discriminant must be accounted for, but superfluous patterns may be present. And exact matches are both sound and complete matches. We derive GSD using the AGT methodology, producing a language that supports a broad spectrum between unstructured and structured data. To generate the gradual language from the static one, AGT instructs us to start by defining the meaning for gradual types via abstract interpretation. Static types, like int, are interpreted as themselves, and in the other side, the unknown type represents any possible static type. In the middle are gradual types like int arrow unknown that represent functions from int to any static type. Now, specifically to the context of data types, closed or open data types, because they are static, represent themselves. Next, to allow for the free manipulation of unstructured data, we realized that the regular unknown type from gradual typing is not enough, and we identified the need for the unknown data type. This type represents every possible data type, open or closed, and place the role of the ground type for constructors. This type is needed to ensure that matches are only performed on constructors and allows us to match on constructors from multiple data types in the same match expression. But this is not enough, and to support unclassified data, a third unknown type is needed. The unknown open data type represents every possible open data type. It performs as the initial type for unclassified data, making them able to inhabit open data types but not closed ones, preserving this way the more structured nature of closed data types. Having the gradual types defined, the rest of the gradualization process is straightforward. The language generated through this process satisfies the desired properties of a gradual language. In particular, it's type safe, it's a conservative extension of the static system, meaning that it behaves in the same way that the static language on fully static programs, and also satisfies both gradual guarantees. As useful as they are, ATTs are a relatively simple feature, and expanding this work to more complicated features like generalized algebraic data types and type classes is an interesting challenge for the future. Also, works need to be done on performance of the implementation, mainly optimizing cost reductions and defining an efficient low-level representation for unclassified data. We also need to explore what will it mean for a real-life statically typed language to support gradually structured data. In summary, we developed JSD, a gradually typed language which supports a broad spectrum between unstructured and structured data and proved its metatheory. The gradualization required the novel introduction of two unknown types, the unknown data type and the unknown open data type. Also, to explore the utility of gradually structured data, we develop an interpreter for JSD that prints the step-by-step production of programs and supports the three mentioned matching strategies. You can find an online version of the interpreter on the URL at the bottom of the screen. Thanks.